Let's talk about a new kind of machine. One that doesn't just get a little bit faster every year. No, this one completely changes the rules of the game. A machine that could make today's most secret codes, well, basically obsolete. We're diving into the wild world of quantum computing.
So, think about it for a second. Every single password, every bank transfer, every supposedly secure message you send, it's all protected. But how, exactly? What is it that keeps all of our digital lives safe from prying eyes? Well, the answer, believe it or not, is just math.
That's right. The entire foundation of our modern digital security is built on a mathematical fortress. Specifically, it's based on a problem that's really easy to state but incredibly hard to solve. Taking a huge number and finding the two prime numbers that you multiply to get it. For a regular computer, that's a practically impossible task.
What if there was a computer that just doesn't play by the same rules? One that uses the incredibly weird principles of quantum mechanics to chew through problems that are supposed to be unsolvable. See, we're not just talking about a faster computer. This is a totally different way of thinking about information itself.
All right, so to really get our heads around this new machine, we have to start with its most basic fundamental piece. We're not in the world of regular bits anymore. We're talking about the quantum bit, or as everyone calls it, the qubit. This little thing is the heart of the entire operation.
So here's where things get really weird and really cool. A classical bit, right? It's like a light switch. It's either on or it's off, a 1 or a 0. That's it. But a qubit, it's more like a spinning coin just before it lands. It's not heads or tails. It's kind of a blurry mix of both at the same time. It exists as both a 0 and a 1, all at once. And that strange property is where all the power comes from.
And yeah, there's a name for this crazy ability. It's called superposition. It's what lets qubits hold and process so much more information than a classical bit ever could. Instead of looking at one possibility at a time, a quantum computer can use superposition to explore a massive number of possibilities all at the very same time.
Okay, so we've got these incredibly powerful new building blocks. But how do we actually control them? How do we tell them what to do? Well, that's where quantum gates come in. You can think of them as the basic instructions, like the verbs in our quantum programming language.
Let's start with a really simple one. The Pauli X gate is about as straightforward as it gets. It's basically the quantum version of a classical NOT gate. So if you have a qubit that's definitely a 0, this gate just flips it to a 1. If it's a 1, it flips it right back to a 0. Easy, reliable, and absolutely essential.
And now for the real magic. The Hadamard gate is honestly one of the most important tools in this whole quantum toolkit. This is the gate that unleashes the power of superposition. It takes a stable, kind of boring qubit that's just sitting there as a 0, and bam! With one single operation, it puts it into that spinning coin state we talked about, a perfect mix of both 0 and 1. This is literally how we kickstart the whole parallel computation process.
So we can create qubits, we can put them into superposition. But the next tool in our kit, this one allows us to link them together in a way that just completely defies our everyday intuition. It's a phenomenon so strange, it honestly baffled some of the greatest minds in the history of physics.
That's what Albert Einstein famously called it. He was really unsettled by this idea of quantum entanglement because it seems to break all the rules of our normal world. And yet, it's totally real, and it's an absolute cornerstone of quantum computing.
So what does this spooky action actually mean? When two qubits are entangled, they stop being independent things. They become a single, connected quantum system. So if you measure one and find out it's a 0, you instantly know, and I mean instantly, that the other one is also a 0. It doesn't matter if it's on the other side of the lab or the other side of the galaxy. Their fates are completely intertwined.
And look, this isn't some random magic trick. It's actually a very precise recipe. We just start with 2 regular qubits, then we use our trusty Hadamard gate to put the first one into superposition. And then we use another special gate called a CNOT gate to link them together. And just like that, they're entangled. We've created that spooky connection completely on purpose.
Okay, so we've got our toolkit, right? We have qubits, we have superposition, we have gates, and we have entanglement. So the big question now is, how do we put all these pieces together to actually solve a problem? And, prove that this whole quantum thing is actually worth the effort.
We're going to start with a classic example. The Deutsch algorithm is kind of like the Hello World program for quantum speedup. It's designed to solve a very specific, almost toy-like problem, but to do it in a way that is demonstrably, provably faster than any classical computer could ever hope to manage.
So the problem is pretty simple.
Imagine you have a black box, an oracle, that does something to an input and gives you an output. You just need to know if the box always gives you the same output or if it gives you different ones. Now, a classical computer has to check it, then check it again. It has to ask at least twice to be sure. But a quantum computer
only needs to ask once. That's it, just one time. By putting the input into a superposition, the Deutsch algorithm is able to check all of the possibilities at the exact same time. It gets the final answer in a single query. And this is just a perfect illustration of what we mean by quantum speedup. It's not about doing the same calculations, just faster. It's about needing fundamentally fewer steps to get to the answer in the first place. For the right kind of problem, that's a mind-blowing, game-changing advantage.
That's a totally fair question. I mean, solving this one little logic puzzle isn't going to break any encryption, but what it does is prove a critical principle. And this is where it all starts to connect.
You see, the very same tools we just used for that simple little proof of concept, the qubits, the Hadamard gates, that amazing power of superposition, those are the exact same building blocks used to build much more powerful quantum algorithms. And the most famous of them all is something called Shor's algorithm.
And here it is. We've come full circle. Shor's algorithm is engineered for one purpose: to solve that impossibly hard math problem that we talked about at the very beginning, the one that all of our modern encryption is built on. So while a classical supercomputer would need billions of years to crack it, a powerful enough quantum computer running Shor's algorithm could do it, well, efficiently. It turns that impenetrable fortress wall into a house of cards.
And that really brings us to the final, and maybe the most important question, because cracking codes is just the beginning. The same incredible power that can be used to break things can also be used to build incredible new things. Just imagine designing new medicines by perfectly simulating molecules, creating new materials with impossible properties, or building an AI that can help us solve some of humanity's greatest challenges. The era of quantum speedup is coming. The only question is, what are we going to do with it?